today's second session of World of Groupcraft 2. We have already 3 speakers, and now the 4th speaker this morning would be Dr. Chandan Maity from IISER Mohali, and he will be speaking on lower dimensional cohomologies of homogeneous spaces of Lie groups. Yeah, over to you, Chandanda. Please start.
Thanks, Sumo, for giving me the opportunity to talk about our work. So my title of my talk is lower dimensional cohomologies of homogeneous space. So the structure of the talk is, first I will give some motivation, and then I will describe explicit formulas of first and second cohomologies of homogeneous spaces with some application to nilpotent orbits. And then we will state some well-known results on homogeneous spaces. We'll give a statement of equivariant Cartan's theorem, and we will apply this theorem to compute third and fourth cohomologies of homogeneous spaces. And finally, we will give some application to homotopic invariance. This talk is based on joint works with Professor Indranil Biswas and Pralay Chatterjee. Yeah, first we will begin by considering some basic examples of Lie groups. So the Lie groups are stated here. I think everyone is comfortable with this. SLNC, determinant 1 matrices, n cross n determinant 1 matrices, SON, C, SP2n, C. So all the SON, C, all the matrices in n cross n complex matrices with the property that G transpose equal to identity. So all the 3 are non-compact. One can prove that these are linear Lie groups, non-compact and simple. Simple in the Lie group sense. Okay, next set of example we will consider which are compact. So S1, the circle group, and then ON, orthogonal group, real orthogonal group. So and then SON, all the orthogonal, special orthogonal, special orthogonal matrices, special unitary matrices, SUN, SPN, UN. So see here, all the groups are compact groups. And also note that for n greater than 2, SON is also a simple, SUN simple, SPN. These 3 are simple Lie groups. But UN is not simple, it has a central torus. So now we will go to some more examples of spaces. All we know sphere, n-dimensional sphere. So this is SN. But one can view in a different way as a homogeneous space. Okay, I will not say the term. Okay, I will come to this term, but one can see this as a coset space of ON modulo ON minus 1. ON is the space of orthogonal group of n cross n orthogonal. This can be seen as a coset space of this SON mod SON minus 1. This RPN minus 1, we know that this is the space of all lines passing through origin in Rn. That also one can see as a coset space of SON modulo ON minus 1. Next, I would like to consider Grassmannian. So this one can see as ON by OR. So R is strictly less than N. OR times ON minus R. So the common thing is that all the spaces are of this is diffeomorphic to the space of coset space G mod H, where G is a Lie group, H is a closed subgroup. So now I will come to the definition of a homogeneous space. A manifold of the form G mod H is called homogeneous space, where G is a Lie group, H is any closed subgroup. See here, I have given many examples of Lie groups, and you can now make any homogeneous spaces. So one can prove that such a coset space has a unique smooth manifold structure. So now our aim is one of the aim of this talk is, so we know that RPN and Grassmannian, they are not homotopic, but can we say by looking at the simple factors of G and H? See, RPN is G SON by ON minus 1. Grassmannian is ON by So in this situation, H is my this one OR times ON minus R. So here I have two simple factors. In that RPN case, I have one, H has only one simple factors. So just by looking at the number of simple factors, can we distinguish such a homogeneous spaces? So this is my question. So I have G1 and G2, H1, H2. So now consider G1 by H1 and G2 by H2. Can we say some necessary condition? When does G1 mod H1 homotopic to G2 mod H2 in terms of the number of simple factors of GIs and HIs? Or in other words, just by looking at the simple factors of GIs and HIs, can we say that G1 mod H1 is not homotopic equivalent to G2 mod H2? Yeah, towards end of the talk, we will give some answer to this question. Now I will begin with some basic stuff. So this is very well-known result on compact Lie groups that so throughout this, the cohomology means I will consider Rham cohomology and with real coefficient. So for a compact connected Lie group, the first four cohomologies can be given in terms of the dimension of center and number of simple factors of G. So now our question is, can we extend such a result in the case of homogeneous spaces? Like what is the dimension of HI of G mod H? Okay, I have, let me give some motivation behind this. So for a semi-simple Lie algebra G, the adjoint orbit admits a closed non-degenerate two form, which is called Poincare form. As a consequence, such orbits has a symplectic manifold structure. Biswas and Chatterjee gave an exactness criteria of the Poincare form for a large class of semi-simple Lie groups. This naturally motivates to the following question: what is the dimension of the second cohomology? Because this symplectic form is a second form. What is the whole dimension of the second cohomology? And this required a general formula for the cohomology groups of homogeneous spaces. So first I will reduce this problem from non-compact type to compact type. So in this situation, so I have L and M are non-compact Lie groups, G or H respectively maximal compact subgroups. Then the natural inclusion G mod H to L mod M is a deformation return. So this result is due to MOS2. So this says that it's enough to look at the compact situation when G and H are compact, as far as the cohomology is concerned with real coefficients. So this is the first result towards this cohomology computation. So let G be a compact connected Lie group and H be a closed subgroup. So we don't have any other assumption. H is any closed subgroup. Then the second cohomology of G mod H is isomorphic to the vector space. So here ZH denotes the center of the Lie algebra H. And so this is an intersection and GG is the commutator. So H by H naught is a finite group which acts on this space, and the first term, this one, is the fixed point under the action of this finite group H by H naught. And the second term is this is a simply vector space, and we are taking the second exterior product. So we have proved that there is a natural isomorphism between these two vector spaces. Hence the dimension, that is enough for the dimension computation purpose. So similarly for H1, we have more simpler thing. So H1 is isomorphic to this vector space G mod GG plus H. So observe that. So we can say some interesting corollaries from here. If G and H are simple, that means G equal to GG. In that situation, H1 of G mod H is 0, whatever H is. And if further H is simple, that means dimension of ZH is 0. In that situation, H2 is 0. So this is the corollary. If G is a compact connected Lie group, H is a closed subgroup. Moreover, assume that G and H naught are semi-simple, then the first and second cohomology vanishes. One can think this as a generalization of Webel's theorem, which says that for a compact semi-simple Lie group, the first and second cohomology of a semi-simple Lie group vanishes. Now question is, can we generalize for the higher thing, like what happened for H3? Yeah, we will come to this question also towards the end of this talk. Now I will give some application of these formulas in the case of nilpotent orbits. I mentioned that nilpotent orbits are, if you take a nilpotent element in a Lie algebra and then consider the natural group action, take the orbit, OX denotes the set of all nilpotent, or so this is equivalently, this is the conjugacy classes of nilpotent element in the Lie algebra SLN8. Then we have proved that the first and second cohomology vanishes. But this is not always the case. For example, if I consider the Lie algebra to be SUPQ, then we have a complicated result, slightly complicated result. It's not always the simple as before. And so basically we have computed the first and second cohomologies for all the nilpotent orbits in classical real Lie algebras. And for exceptional also we have some partial results. Now the natural question is, what can we say about the higher cohomologies of G mod H? Before going to that, let me state some well-known result on the G mod H so this is a result due to Borel, who says that G is a compact connected Lie groups, H is a closed subgroup. Also assume that the rank of G and H are same. That means G and H admits a common maximal torus. So in this situation, the Poincare polynomial, Poincare polynomial is a polynomial whose coefficients are given by the Betti number of the corresponding manifold. So in this situation, Borel proved that the Poincare polynomial, the coefficient of the cohomology, the dimension of the cohomology is given by this formula. So this is indeed a polynomial, and here this SI, RI, they are given by the cohomology of G and H. So now, this is a slight variation of a particular case of a Cartan's theorem, which I am going to describe. But before describe this Cartan's theorem, we need some terminologies. So here, let me explain this term SG star. So this is the symmetric algebra over G. And so let me come to this blue color thing. So this is a Koszul complex which consisting of SH star power H. Power H means this is H invariant thing. So H not invariant symmetric polynomials. So this complex consisting of two things. First one is the symmetric part. Second part is the exterior part. So H star G, this is the exterior algebra. And equipped with a differential nabla. So nabla is a differential which is defined here. So this is a Kochen complex. One can prove this is called Koszul complex. Cartan's proved that. So before going to Cartan's theorem, so here I have written some initial terms of this object. So the first term is like this, and also I have explicitly write down some the maps, what the differential maps in the lower dimensional situation. So Cartan proved that the cohomology of that Koszul complex is isomorphic to the cohomology of G mod H naught. So G be a compact connected Lie group, H naught is the connected Lie subgroup. So in this situation, the cohomology of G mod H naught is given by the cohomology of this Koszul complex. Now the question is, what happens if H is not a connected thing? H is a disconnected one. So we have proved that this theorem is in fact H by H naught equivariant. So here is some maps. So Cartan proved that this is in the H0 level, but we have proved these maps are H by H0 equivariant. That means we now in this theorem, G is a compact connected Lie group. H is any closed subgroup, not necessarily connected. Then the similar isomorphism hold. This is the isomorphic. This isomorphic to this is H star power H. That means I am considering here capital H invariant symmetric polynomial. So this complex will give me a cohomology ring of G mod H. But still, the right hand side is quite complicated object. So can we simplify it? So what we have done it, we consider this complex. So this the maps are given here, and we apply it to compute third and fourth cohomology in an explicit way. So okay, before going to there, I need some more terminologies. So here we define a couple of vector spaces which will be required in this sequence. GBA compact connected Lie groups. H is a closed subgroup which is not necessarily connected. S to GG star power H, that means I am considering symmetric two form which are also G invariant symmetric two forms. Now note that H intersection GG, this is a sub of GG. So I can restrict my form on this. So this is simply the restriction map. Now I am considering the kernel of this. Just I would like to mention one thing. If G is simple, then this dimension, this is a one-dimensional thing. The killing form will give me, killing form is the only non-element in this space, and this is one dimension. If G is semi-simple with k many simple factors, then the dimension of this S2 of G star G is going to be k, the same as the number of simple factors. And in fact, the killing forms on each of the simple factors will give a basis of this vector space. Okay. So NGH is kernel of this restriction map, and CGH, this is the co-kernel of this map. Yeah. So after, the theorem is G be a compact connected Lie groups, H be a closed subgroup, and R0 denotes the dimension of these vector spaces. Then the following isomorphisms. So H3 of G mod H is isomorphic to the following vector space. So the right hand side is ZH intersection GG star. So as before, this is you can treat it as a vector space and a finite group H by H not acting on this. So we are considering the fixed point of this vector space. And so this is tensor. So even think this part, this term is coming from the second cohomology thing, and so this G by GG plus H star, it's coming from the first cohomology. So that's why it has a contribution to third cohomology. Similarly, for the last term OS3, the contribution came from the first cohomology. But NGH is a genuine term in this situation. So NGH is defined here, the kernel of this restriction map. Similarly, we have a nice description for fourth cohomology for a general in the general setup. So this is the in the similar way, the first and last term are coming from the lower dimension situation, but this NGH power R0 and CGH. So it is a genuine term which so CGH is defined as before here as a co-kernel of this map. So the proof is it's coming from the equivariant Cartan's theorem, and we explicitly identify the kernel and image of the respectively the differential of this Koszul complex. Okay, but instead of going to the proof, I will show you some nice, interesting application of these two theorems, of this theorem. So first one is here we are restricting ourselves into some semi-simple situation. A GBA compact connected Lie group H is a closed subgroup. Moreover, assume that G and H not are semi-simple Lie algebra, which is equivalent to say that the Lie algebras of G and H are semi-simple. H may be disconnected, but it's Lie algebra. So basically, H has a discrete center. Then this equality holds. This is that the difference of the dimension of fourth and third cohomology is given by the difference of number of simple factors of G and H. So H, if H is semi-simple, then one can write H as direct sum of H1, H2, HR, and G similarly one can write as a number of simple factors. So one can count the simple factor. Okay, let us take this example. So here I am considering G to be SUN, H to be as a block diagonal SUR, SUN minus R, and consider G mod H. So from this corollary, we can say that the dimension of the difference of H4 and H3 is 1. So the advantage of this theorem and the previous one is that you don't have to go to the differential form business. So simply by looking at G and H, one can say it's one can say the dimension of the cohomologies. So yeah, so by simply looking at simple factor, we can say in this situation we can able to say that so the next corollary is also quite important, and it has an application to the homotopic invariance. So observe that suppose I have two set of homogeneous spaces, G1 H1 and G2 H2. If they are homotopic, then the difference of dimension of H4 and H3 must be equal, which says that the difference of the dimension of the number of simple factors of H and number of simple factor of G must be constant. So this is the corollary what I am talking about. So G be a compact connected Lie groups, Hi inside Gi be a closed subgroup, Gi so assume also Gi and Hi not are semi-simple Lie groups. Suppose this difference of the number of simple factors are not equal, then G1 by H1 cannot be homotopically equivalent to G2 by H2. So therefore that will give just by looking at the simple factors that whether G1 by H1 cannot be homotopically equivalent to G2 by H2. For example, just recall the example in the Grassmannian and real projective spaces. Okay, yeah. See, so in this situation, so H has only one simple factor, but in the Grassmannian situation, we have two simple factors. So therefore, from that corollary, we can say that they cannot be homotopically equivalent. Okay, so if the second thing is if they are homotopically equivalent, then the difference of number of simple factor must equal. Okay, finally I will give some more application towards this vanishing result of third cohomology of G mod H. So this result is due to Hasan Azad, and this also follows from our theorem. It says that if G is a compact simple Lie group and H is a closed subgroup, assume that it is a positive dimension. That means we are not using H to be discrete. It must have a positive dimension. Then the third cohomology of G mod H is 0. So yeah, now we can say little bit more about third and fourth cohomology explicitly in the following cases. So suppose G and H, G be a compact connected Lie group, H is a closed subgroup. Assume that as before G naught is simple. Let L be the dimension of ZG and R be the number of simple factors. In that situation, dimension of H3 of G mod H is given by this R minus 1 plus L choose 3. So that you can think that there is in the theorem there is a exterior product there. And similarly for H4 we have a explicit description that a dimension of H4 is equal to R minus L power L plus L choose 4. So this is the without going, but we can say that by simply looking at G and H and its simple factor, we can say the dimension of the cohomology of G and H. Yeah, thank you. So here I have some references. So basically, so this is the paper mostly for lower dimensional cohomologies of homogeneous spaces. And yeah, here is some references. I would like to stop here.
Yeah, thank you, Chandan. Any questions? Okay, if not, let us thank the speaker again. Yeah.